This is our third unit. In our first unit, we talked about the basics of the Arduino. We looked at the basic functions, the basic Arduino IDE, and how to use all of those functions in their most basic way. In the second unit, we delved in a little deeper and we talked about how to do a lot of the same kinds of things you could do in the Arduino IDE now using C, and we got deeper in the sense that we got into some functions that you cannot do in the Arduino IDE. And so we got deeper. Now we're going even deeper. Okay, and we're now talking about the assembly language, which is not quite machine language, but it's really close to machine language for the Arduino IDE. And so that's what we're looking at in this lecture and in this unit. So first we're going to talk about the motivation behind using the assembly language. Next we're going to talk about the scheme of the assembly language, where assembly language fits in. Then we're going to talk about the assembly language environment. What is the environment needed to be able to do assembly language on the Arduino? And then we're going to look at some sample codes just to kind of get our feet wet a little bit with this subject. So, the motivation behind assembly language. Why learn assembly language? Why learn? Sometimes it'll be called assembly, sometimes it'll be called the assembler, assembly language, a lot of different names for it. But here are some reasons. One is that you can directly analyze for bugs. So even if your program is written in the Arduino IDE or in C, you can do what's called the disassemble the code into assembly language, and you can check to see what's going on. It's possible sometimes you can write C code that when you compile it, it actually changes the behavior. The compiler changes the behavior of what the C code is intended to do, which is kind of weird. Now, it turns out those are mostly academic types of situations, but it can happen in real applications. So it's important to understand when this could be an issue or not. So in that case, in the disassembler, you can actually analyze for bugs. In assembler, you can also understand why a program executes differently than designed, for example, which is basically what a bug is. Also, often higher level languages don't support all the hardware features of the processor. And then of course there are time critical routines. In assembler, you can write the routines as quickly as possible to operate. In the assembler, code is short and easy, so that's always good. Code executes as fast as possible. That is, you can write the code to execute as fast as possible. And with each instruction that you give in an assembly program, you can actually count the number of clock cycles. So each instruction, you know exactly how many clock cycles that particular instruction is going to take. So you can optimize things in terms of their actual clock cycles. So with C and with the Arduino IDE, there's no way you can see that kind of information. So you can get it as fast as possible on that processor. So not as fast as possible with any processor, but at least with that processor, you can get it as fast as possible. Also, assembler is easy to learn and fun. Also, the code can take full advantage of all the hardware features. And finally, learning assembler allows us to understand all the compilation process of a program, otherwise known as calling conventions and things like that associated with the microcontroller. So, learning assembler for one processor makes it easier to learn another dialect. So, the Arduino is just a microcontroller. It's not necessarily the best microcontroller at necessarily anything. Okay, There are some microcontrollers that are simpler to use. There are some microcontrollers that are faster. There are some microcontrollers with more inputs and more outputs. The Arduino, there's nothing magical about the Arduino itself. It is simple, one of the simpler. It's got some nice tools. It's, there are a number of reasons why, and we've looked at why using the Arduino. But one of the things that you can do with any microcontroller is learn its assembly language. And the process of working with assembly language in for one processor is very similar to what you would do for another processor. A lot of the same kinds of things come. So, by learning the assembler, you simultaneously learn in depth the hardware. So up to this point, we've actually seen a lot about the hardware, a lot of the registers, a lot of the different things you need to set this before you set that, and so forth, the procedures that need to take place. There's even more that we have yet to learn. And not just because we haven't looked at all the possible registers and so forth. There's certainly that. But also, there is even more to the whole process of working with the hardware than even that C masks. So even the C compiler, as simple as it is, masks certain features of the hardware. Also, code is simpler, and the code always does what you ask it to do. Okay, it always does exactly what you ask it to do. It's very simple. Every step by step, it does exactly what you want it to do. Okay. Oh, also, did I mention it's fun? Okay. The code itself, when you get the code, you can get it optimized for not only speed, but also for space. In general, a assembly language program has as small a footprint as you can get for any kind of code for a particular processor. In that sense, the assembly code is naked. There's nothing hidden. There's no surprises. Okay? What you see is what you get. And as a result, it allows for exact algorithm analysis. So, for example, I mentioned you can do what's called a core dump that can be used with the assembly to debug a problem. We're not actually going to get into doing core dumps because that's like another thing to have to learn, but it's not too far afield from what we're talking about here. It's just a little bit further afield than I want to go. If you want to learn more about how to disassemble code, you can look up online, and there are plenty of sites that'll tell you how to do that. Also, again, timing for certain functions can be attained by counting the number of operations required to fill it. So you can know exactly how long a particular procedure is going to take. So, again, why learn assembler? Well, for one thing, it enables noob programmers to become experts. So when you can do assembly, you are an expert in that particular processor. Also, assembly language programmers earn more. That's not a bad thing, right? Did I mention that assembly writing language writing is fun? And fun? And of course, it's very important that it would allow programmers to look like cyber geeks. See, now, when I was a student, a cyber geek, a geek of any kind, was just basically a nerd. But now, it's like cool in some settings to be a nerd, which is kind of weird. But anyway, that's life. So it can allow you to look like a cyber geek, a true cyber geek. If you can do assembly language, you can talk shop with even the most intense programmer. What are applications for assembly language? Well, device drivers. So device drivers basically is a way of connecting very closely with a specific device to communicate with it and to work with it to do what you want it to do. So the basic idea behind a device driver is that you would have some high-level program that would call a subroutine that would access that device. And so we've already seen, in a sense, a lot of what we've been doing is in fact writing device drivers. Also, you've used device drivers in a sense by calling libraries, for example, the servo library or the library that we saw using stepper motors, things like that. There are libraries that can be used to basically make the connection between a high-level program and a low-level program. It can be used for low-level embedded systems. There are lots of different applications for low-level embedded systems. It can be used for real-time systems where again it's time critical, and so you need to make sure that things happen exactly when you expect them to happen. It can be used for speed critical systems when obviously you are constrained to use a certain microprocessor, and that microprocessor has limits, and so you want to be able to push the limits of that microprocessor. It's also used for space critical systems. That is where you only have limited amount of memory, and so you need to optimize the amount of the footprint of your code in the memory. Also, using assembly, we can actually allow for some certain amount of parallel processing even on a non-parallel machine. That is, your assembly language can be so fast you can actually be setting it up to do two things at the same time. Actually, it's not really at the same time, but you can intersperse doing this and doing that, doing this and doing that in your code in a way that makes them appear to be operating at the same time. Now, we've been using C, and C is not assembly, but in some cases, C can actually be pretty close to assembly. For example, both can access all the functions and registers of the ATmega 328. So with C, we have seen how to do that. C also can have a decidedly smaller footprint in terms of code than the Arduino IDE. And with C, and of course assembly, you can have some time-sensitive functionality. You can set things up to be time-sensitive. But there are important differences between C and assembly. In assembly, we will work with things like the program counter and the stack. That's definitely something you don't do in C. It's not that you couldn't, but the C environment itself does so much. It actually does that for you in some ways, but doing it for you means that you don't get to do it directly yourself. You don't do direct access to it. So those are a couple things: the program counter and the stack. So in C, we haven't even talked about the stack. You could look at the program counter, but the stack is almost meaningless in C. You could use it in C, but it's almost meaningless in C. In assembly, there are no predefined data types. You need to define the data types. You need to, and you can define them, but it's not the same. So you can't just define an unsigned int. It's not just defined already. Okay. Also, in assembly, you work directly with addresses a lot more and pointers. Okay. So these are some important differences, and we'll definitely see more as we go along. So, where does assembly language fit into the scheme of things? Well, in Arduino, we've actually been using assembly quite a bit already, even though you haven't known it. There is a process by which our code goes and it uses assembly language. So we start off, for example, with a C file or an INO file or a C++ file. Okay, so you can use these files along with their headers, associated headers. They go into a preprocessor. Those preprocessors work with these files to create a .i file or a .ii file. Those files are fed into a compiler, and that compiler actually generates an assembly file. So here I've shown .small s. The Arduino IDE generates a .large s. That goes into the assembler. The assembler then takes that file and creates a object file, .o file, which is like a precompiled file. That goes into the linker. The linker will combine that file with other files, command files, other object files, other library files. Okay, it'll generate a file map, which is used for reference, but it also generates a file out. And then that file goes into a converter, and that converter may be used to generate a number of different other files, executable type files. So for example, exe files, elf files, and so forth, hex files. So notice assembly is not actually the end game. The assembler may be used by the linker in order to combine other libraries and things together to create the final executable. Okay, and so this is actually the final binary file that comes out. There may be a number of different formats that are used. Okay, so, but the assembler is part along the way. So the assembler actually is not machine code. The machine code is very closely tied, however, to the assembler. Now, the hardware. It's important for us to understand the hardware in working with the assembler. So in the hardware, we have the central processing unit, which may contain an arithmetic logic unit. There are also a diverse number of storage units, registers, EEPROM, flash memory, so forth. And then there are ports that control the peripherals, the GPIO, the timers, the other devices. Okay, so this is the hardware. We've already looked at a lot of this already. Okay, so how the CPU works. Basically, the CPU reads an instruction, which is called an instruction fetch, from program storage. Then it loads data from data storage into the necessary registers, executes a command, and continues on. Okay, so those are the kinds of things that happen. Just to kind of give you a taste of what some of these things look like, here's the CPU operation. Here's the binary version of the code that's used. Notice that there are 2 bytes of data. So the code in binary might look like this. The code in hex might look like this. So put CPU to sleep. That instruction has this particular code. Add register 1 to register 0. It has this particular code. Subtract register 1 from register 0 has this code. Write the constant value 170 to register 16. It would have this code. Notice that this instruction actually embeds the number 170 into the instruction. Okay, so that is the write to a register. That instruction actually has space within it for the number that you would put. And then we have multiply register 3 with register 2 and write the result in registers 1 and 0, the most significant bit and the least significant bit. And so here is the instruction for that. Okay, so this is actually the machine instruction. Okay, this machine instruction, for example, might include data and register number. And so it's very explicit. This instruction, that the processor knows exactly what to do with that instruction. So an example here is we want to add register 0 to register 1. So if you look back here, add register 1 to register 0, notice this is the hex code for that. Okay, so here's our program counter. Our program counter encounters this instruction. So it's going along. We have a set of instructions. The program counter is pointing at this instruction. This instruction goes to the arithmetic logic unit. The arithmetic logic unit knows then it needs to grab registers 0 and registers 1, okay, put them together, and then add. Okay, so it takes the 2 values in these 2 registers and add. So when it adds, it puts the result in register 0. So it knows that it's going to take these 2. So notice it takes register 0, register 1, adds them, puts the result back in register 0. So register 0 is now changed. Register 1 actually remains unchanged. So that's the kind of thing that happens. And so that's the process for each each instruction follows a very similar process. Okay, so this this goes into register 0, and then our next instruction comes along. We may then put register 0 somewhere else, or whatever the next instruction is. Okay, so that's the flow for how an assembly code goes. There are various classes of operations. Just like with C, you have various kinds of operations. You have arithmetic, logic instructions. You have branch instructions. So with C, you have like if, this, then, or you have do while or case. You have branching instructions, bit and bit test instructions, data transfer instructions, microcontroller control instructions. And the codes are often given in mnemonics. That's like a short, it's like an abbreviation for the code. And so when you look at the instructions, they're all, LDI, SBI, CBI. They're cryptic by themselves until you learn what the abbreviation stands for. Operands, data that the operation operates on are called the operand. So for example, we saw the addition, okay? And so we saw the addition of register 0 with register 1. Register 0 and register 1, those two things are called the operands. The operands can be register values, they can be memory, or they can be data, or direct data. Okay? So data must be put into specific registers in order to be operated on or executed. The Arduino operations use at most 2 operands. You don't ever have any instructions that require 3 or 4 operands. So whenever you do things with at most 2 operands. There are a number of possibilities when it comes to the input and output command schemes. And we're going to see this as we go through and we look carefully at all the various commands that are available in the ATmega 328. And we'll do that in the next lecture. We'll look at those in specific, many of the specific instructions. But for now, I just wanted to point out that you could have, for example, an instruction that requires 8 bits of data and returns 8 bits of data. You can have an instruction that takes 2 8-bit inputs, operands, and returns 1 8-bit result. You can have a function that takes 2 8-bit operands and returns a 16-bit result. For example, multiply. If you take 2 8-bit numbers and you multiply them together, in general, you'll get a 16-bit number. So that would be an example here. Or you can have 1 16-bit operand and get a 16-bit result. So those are some possible input-output command schemes that you could work with, which is kind of weird. It's like, well, how can I get 16-bit results? Well, that just means you're getting a high byte and you're getting a low byte. And there are specific registers that work with 16 bits of data. Okay, so we'll come to that later, but for now, just understand that these are some possibilities that can happen. How is data included in a command? As I mentioned, for some commands, data is actually embedded in the command itself. Okay, so here's the command, load immediate. That's what this stands for. Again, that's the mnemonic. Load immediate R, C. So R is the register, and C is the data. Okay, so remember R has there are only certain numbers of registers. Okay, so even though I have R here, R is a register. There are only a finite number of registers, actually 32 registers. So the number of bits for the registers is 0 through 3. Okay, so that's where the register values go. And then the constant values, the value you're going to load into the register. Notice here here's the low byte and here's the high byte. And then these numbers here indicate that you're going to do this load immediate command. Okay, so this command, when you convert it to machine language, which is just 1s and 0s, you can see how the 1s and 0s fit in to the command itself. And so this part over here indicates that you're doing this kind of a command. Okay, so notice only 4 bits are used for that. The rest is used for the data and for the register number. Okay, so crazy, huh? It's crazy to me that they would put the register in, kind of throw it in the middle here, but anyway, that's what they do. Okay, so here is an example subroutine. Now, whenever you have a subroutine, you have what's called a label, okay, which is basically starts on the left-hand margin, and it ends in a colon. Okay, so that indicates a label. And in the Arduino IDE, when you look at your .s file, when you look at your file that has the assembly in it, this will actually be a different shade than the rest of the code. And then you have these code. You have this code, and here are some things that you can do with this. So load immediate, register 18 with this pin mask, and so forth. So this is an example. So this is the entry point for the function, and then you return. Now notice when you, unlike C, when you say return something in a C program, you would say return blah blah blah, right? Well, here notice there's no void, there's no nothing that indicates the data type. So remember I said the data types are not defined. It's not defined here. It's just an entry point. Okay, so the data for a subroutine needs to be put into special places before it can be used in that subroutine. And likewise, it will, when you return, the data that you want needs to be put into the appropriate places before you do the return. So this is the return. Okay, so that's an example subroutine. Okay, now again, when you first see this kind of code, it looks very Greek. I mean, load immediate, and sometimes I even forget the names of what some of these codes mean, the names exactly. So hopefully you can remember the important ones. We'll look at a lot of them in detail in the next lecture. So again, you have mnemonics for the machine instructions. You have the register names, registers 0 through 31, so again 32 registers. In your program, you have what are called directives. Directives do things like create data, specify addresses, determine what header files will be included, and so forth. Define global variables and stuff like that. Symbols are the names for values or addresses. Okay, so the actual machine language has no variables. It's just ones and zeros. But in assembly, we can actually have labels which actually have meaning in terms of, like, this is a line of code and we're going to go here and so forth. And so the assembly language is not machine language. It is, we saw it's above machine language in terms of being more abstract than the machine language. The machine language is absolutely concrete. That's exactly what, when the processor sees that combination of ones and zeros, it knows exactly what to do. Okay, the processor doesn't know anything about subroutines. It doesn't know anything about that. It only knows ones and zeros. Okay, and when it gets this command, it knows what to do, and so forth. So symbols. You also have syntax that specifies addressing modes. We're going to talk about that later. We have numerical values that can appear in here, and again, you can express them in terms of decimal, binary, or hex. And then you can also, like other programming languages, you can also have comments. Okay, so in terms of the assembly language code forms, every line of code will be like one of the following. It'll be one of the following types. It'll either be a directive, okay, it'll be an instruction, it'll be a comment, or it'll be an empty line. That's it. Those are the only possibilities. Each directive may have a label that defines it. Each instruction may have a label that defines it. The directives may have operands, and you could also have a comment. The instruction might have operands, one or more operands, and it may also have a comment. So that's how the code looks. You have those kinds of lines. Okay, so Generally speaking, in assembly, lines should be limited to 120 characters. Now, the actual instructions themselves can be represented generally by as few. The longest instruction can be expressed in terms of maybe 10 characters. Okay. Now, you can obviously make them longer if you've defined labels, and so then you have labels that represent certain things. But you could actually express that same thing in a lot fewer characters. So the actual instructions are actually quite short, but the line could be up to 120 characters if you choose to have a long comment, for example, or if you choose to have labels and things like that that are long. Okay, so it's generally assumed that you will limit lines to 120 characters. Labels are generally an alphanumeric string that end with a colon. The labels are generally targets for jump and branch instructions. Labels are also maybe used for variable names in program memory and RAM. Okay, so you can actually define a variable using a label. Comments can be written in a couple ways. One is to use the semicolon followed by text. So any text that follows a semicolon will be treated as a comment. The pound symbol is kind of a weird symbol in that sometimes it refers to a comment, sometimes it actually is used for directives. So that's kind of a weird thing. So generally I recommend if you're going to do a comment, use the semicolon. Okay, it's a lot more clear than using the pound sign. The pound sign, like I said, can mean some different things. Here's some example assembly code. And we'll definitely be getting lots of example assembly code as we go along. Again, at first it looks very strange, but there is method to this madness. So in this particular case, we have a label, and we have here what are called directives. Okay, so these are directives. These are not things that actually get executed. These are not converted into executables. These are used for things like definitions. Okay, so for example, I'm defining for purposes of our assembly code some variables. Okay, var1, var2. This directive puts the value 100 into this. So wherever in my program I use var1, it will mean 100. Wherever I have var2, it will mean 200. Anywhere else I have these used in my program, they will have specific meanings. So you can define registers and give them a name. You can name things and in that way, and you can define constants and things like that. And so that can be helpful in terms of your overall program. So those are directives. Next we have instructions. Again, here we have a label and then some instructions. So no op means it's not going to do anything. And then this relative jump test. So it's going to jump back to the, this instruction says it's going to jump to the label test. So it's going to jump here. And so you can see here, this is an infinite loop. These are comments over here off to the side. Okay, and so this is basically going to just go around and around. Okay, I can have pure comment lines. Here's another comment line. So this is an example of assembly code. It's fairly simple. Each instruction has specific meanings. As I mentioned, instructions often have operands. And so here are some of the forms for operands. These are, when you get into looking at some of the different instructions, it's going to ask for operands, and there are a number of symbols, and it's like, what does that symbol mean exactly? And so forth. Okay, so it's helpful to have at least have certain references like this available whenever you're looking at a new instruction. Okay, for example, there's the instruction guide, the assembling guide, and it tells you how to use every single instruction, but you have to understand what the symbols mean. So here, for example, R sub RD stands for a destination register. So that's where the data is going to go when it executes the command. So for example, when you take register 0, add register 1, it's going to put the result in register 0. Register 0 is the destination register. It also may be one of the operands that's the two data things that you put in. Okay. Then in general, you may also have a source register. So if you have an instruction that requires two operands, generally speaking, one of them will be a destination register and the other will be a source register. And again, these can be any of these registers. So in particular, they can be registers 0 to 31. Okay, so any of those registers. B stands for a bit in the register file or IO register. Okay, so that's a 3-bit. The IO register is a 3-bit constant. Okay, so it's a bit. So in a register, S is for a bit in the status register. There is a specific register that's called a status register, or SREG. And so that's a bit in the status register. X, Y, and Z are 16-bit registers. X, Y, and Z. There are 3 16-bit registers, X, Y, and Z. They're actually addressed indirectly. So X, Y, and Z are their indirect addresses. Their direct addresses are, for X is register 27 and 26. Notice that they go in descending order. That's the high byte, that's the low byte. So it makes sense, but it just looks strange when you see it instead of 26 and 27, right? And then so that's X, that's Y, and that's Z. So you can see from registers 26 to 32, that should say 30. From registers 26 to 31, we have these registers defined, 16-bit registers. So basically 2 8-bit registers. The symbol K stands for constant data, where capital K, lowercase k stands for a constant address. Okay. A, when you're looking at the operands, stands for an IO location address. Q stands for displacement, for direct addressing. And PC stands for the program counter. So that tells us what's going to happen with the program counter. So those are the operand forms. So what could be used as an operand? So as I mentioned, there are a number of different types of instructions. Those instructions might use operands. There are different kinds of things that can go into operands. Here are some of the things. You can put in a label. For example, the value of the location counter at the place where they appear. So, for example, jump. We saw the command rjump, and then there was a label. So a label could be used as an operand. Variables could be used as an operand. So you can define a variable using the .set directive to define a variable. You can define constants using the .equ directive. So these could go in as operands. You can put in integer constants, so you can put in decimal values or hex values or binary values. You can insert any of those in for operands. So in the simplest case is actually to use data to go into an operand. That's the simplest case. You can almost always use constants to go into an operand. So that constant can be a register. Okay, that constant can be of data. Okay, so incidentally, for hex, you can use either the X notation or the $ notation. Sometimes you'll see it, well, either way. And then the other thing you can put in is the program counter. So any register, for example, can be listed by its address. Okay, so any register can go in, or by a label, or by a variable. And then program counter can also go into an operand. In terms of operations, what can you do? Here are some of the operations, and again, these kinds of operations are very similar to what we have in any kind of programming language. We have the logical not. So if it's 1 if the expression is 0, it's 0 otherwise. So that's the logical NOT. This is a bitwise NOT. So if you have a byte, this NOT will give you take the inversion of every bit. Okay, here's a unary minus. That's what you use to create a negative number. Multiplication, division, addition, subtraction. Now these operations have priority. Okay, they have priority. So by that, the instruction with the highest priority is going to be executed first. That's kind of like algebra. In algebra, there is the acronym PEMDAS, right? Powers and exponents, multiplication, division, addition, subtraction. PEMDAS. And so that shows the priority. So if you have, for example, 3 plus 2 times 4. So the multiplication has higher priority than the plus. So the multiplication is going to be done first, and then the addition, even though the addition from the left to right order, the addition comes first. So in the same way, these three expressions, these three operations have priority. So if you have A and not B, the not is going to be done for the B before the AND is done, that kind of thing. So, so there's priority. Okay, and so you can see the priority numbers, addition, subtraction. There is a shift left, shift right, just like we had before, less than. Okay, here we have more operators. We have, for example, these comparison operators. Less than or equal to, greater than or equal to, equal or not equal. These three have the same priority. These two have the same priority, which is less than this priority. Okay. Then we have bitwise expressions and exclusive OR and OR. Notice that these have priorities, definite priorities. And has higher priority than exclusive OR, and exclusive OR has higher priority than OR, which is kind of interesting. And then you have logical operators, or what are sometimes called Boolean operators, and and OR. So if you have two operands, then the AND is true only if both operands are true, and with an OR, they're true if either operand is true. So we have these definite priorities for these operators. Okay, directives. Directives are not directly translated into opcodes. They're used to do things like adjust the location of program in memory, define macros, initialize memory, define variables, and so forth. Here are some directives. There is the byte directive that reserves a byte to a variable. There is the COM, which declares a common symbol. So this is often used in working with global variables. We'll come to that in just a minute. Data specifies a data section of the program where data is defined. If-def. So this is used to tell the assembler to include the following code if the condition is satisfied. Else tells the assembler to include the following code if the if condition is. So if-def, then you do this. Else, you do this. So it's in a sense, even the assembling of code together can have conditions based on it. So if this is defined and that's not defined, and so forth, then we can do it that way. Include is like a C include. It'll include supporting files. Notice that you can either use the dot or the pound. And for a lot of these directives, the pound actually works similar to the dot, but they're not the same. And to be honest, I don't know the difference between the dot and the pound. Maybe someone that's wiser than me can fill me in on that, but I don't know. But anyway, sometimes you'll see in code that they'll use the pound, sometimes they'll use the dot. We also saw that sometimes the pound can be used to identify a comment, and so there's a little bit. I'm a little bit confused about the pound. I'll probably figure it out one of these days, but I don't know right now. And then .file specifies the start of a new logical file. Here are some more directives. The .text assembles what follows onto the end of what's called the text subsection. Okay, so a program can be defined up into various sections. You can have a data section, you can have a text section, and so forth. So the data section and the text sections are the two main sections that we would work with. Global defines or acknowledges a global variable or subroutine. A subroutine generally will need to be defined as a global, and it's often used with a variable specified by .com. So .com is one way of working with variables. .extern basically treats the symbols as external symbols, which means they can be accessed and, or come from other sources than the local program. Space can be used to allocate space for an array. Okay, so the .space. .equ defines constants for use in a program. .set defines what are usually local variables in a program. If you want a global variable, you generally need to use .global, and you generally need to use .com for those. Okay, so these are some of the directives. The GCC actually defines a whole slew of directives. Lots of directives. I probably know what a third of these directives even mean. There's a lot of stuff that you can do. A lot of directives. And again, these do not translate into opcodes. These are just to help the assembler know what to do with whatever's connected to these directives. So there's probably a lot of useful stuff that I'm just not aware of. So I have a lot to learn, just like you have a lot to learn in this subject of assembly. It's a deep subject. Deep subject. Okay. Now, in order to use assembly language for the Arduino, we need to establish or set up the assembly environment. So basically, the Arduino IDE doesn't directly allow assembly language, but there are a number of approaches that exist to do assembly language with the Arduino IDE. Here are the three main methods of working with assembly language. First is to modify the Arduino IDE, to modify the IDE. Second is to do what's called inline assembly. And third is to actually use a third-party IDE called the AVR Studio. Okay, so, and I have these listed in the order that you probably ought to consider using them. That is, I would recommend, first of all, modifying the Arduino IDE. This is what we're going to pursue mostly here in this presentation. Inline assembly has its value, and I'll talk a little bit about that. And then finally, the last is to use the AVR Studio instead of the Arduino IDE. The AVR Studio, or TOOLCHAIN, is very rich. There is a slick integrated environment in Windows. Windows is the only environment that you have, the integrated environment. You can still use the TOOLCHAIN in Linux and in Mac. You just don't have the nice integrated environment. So that's another reason why I am not opting to recommend this approach, because many people use Linux, many people use Mac, and so it's very limited to use this as a tool. So I'd rather not teach this as a tool, since it has its limitations that way. But you can directly incorporate assembly in your code. Generally, also using Amtel Studio requires knowledge of the bootloading process. So you don't have to use Amtel Studio. You can still use the AVR TOOLCHAIN in Mac, Windows, Linux. You can use the same TOOLCHAIN, but you have to use it in a command line structure. And again, not so pleasant for anyone but the Windows users. Not so pleasant. It's not so bad. You can learn how to use it, but it's definitely a steep learning curve. So I say this is for the power users. Okay, for power users. If you're going to be doing a lot of development in assembly, then you probably want to consider going in this direction. For a Mac, you can use something like Boot Camp or one of the virtual machines like Parallels or VMware Fusion to emulate the Windows environment and then load this into that and so forth. So you can still use this on a Mac if you use a Windows emulator. But again, this is not the one I recommend. The other one, another option is the inline assembly, which basically allows for all the assembly commands and structures, but it requires a lot of extra stuff in the code to support the program. It's not a part of the program, and as a result, it's more difficult to read and debug. It's not elegant, but it is usable. So here's an example of how a command that we would have for assembly using inline assembly. So ASM indicates that we're going to use an assembly code, and then we have a number of things separated by colons. Okay, so the ASM indicates that that assembly is being used. Then you have this assembly instruction. So we've seen these kinds of instructions already. Okay, and notice that along with this instruction, which is in quotes, we need to have these escape characters, \n, \t, kind of like we have when you format C code, okay, to give you a carriage return line feed. Okay, and notice that this requires an input parameter and an output parameter. Then you have the list of operands that follow, okay, and in general they may be separated by commas. In our case, we only have one, so it's not separated by commas. And then you have the output, which again is, you may have multiple outputs, and again they're separated by commas. In this particular example code, there's only one, so they're not separated by commas. Okay, so commas separate things between colons. Okay, well, this is actually the approach recommended by our text, and again, it is useful in some settings. In particular, it's useful for incorporating perhaps a single command or a couple of commands. Okay, so sometimes you'll see on the web when you're looking for how to do certain things, especially learning how to do in assembly, often they'll include some inline assembly instructions. Okay, but in general, it's not practical for code of any length. It becomes very cumbersome after a while, and it's just not elegant. So I'm not going to pursue that. So instead, I'm now going to pursue modifying the IDE. Modifying the IDE. So the Arduino IDE is in fact open source, which means that anyone can modify it for their purposes. Okay? The source code is also freely available. But to modify the IDE, we have to go through a process. And it's a process you don't have to do all the time. It's not like you have to do this every time you're going to do an Arduino program. In fact, you may only have to ever do it once. Okay? So the only time you ever need to do this is if you ever want to upgrade to the latest version of the Arduino IDE. But for example, if you're using the Arduino Uno, the current version of the Arduino IDE will probably last you the rest of your life, or as long as you're ever going to use the Arduino IDE. So it's not like you have to upgrade. The upgrades for the Arduino IDE are primarily to incorporate new and different kinds of Arduinos. The Arduino IDE, the Arduino INLINE, the Arduino, Explora, and so forth. There are a number, they're continually coming out with new Arduinos, and as they do, they need to incorporate new features, and so those new features then require the latest version of the IDE. But if you're just using the Arduino Uno, for example, then you don't have to keep upgrading your IDE. There's no reason to. If it works, it works, and it's not like any of the changes they make are going to substantially affect. They're always going to be backwardly compatible. So if we're just using the Arduino Uno, that is pretty well set as fixed as a platform. So again, you probably only need to do this once. So in terms of modifying the Arduino IDE, the Arduino IDE actually uses the GCC process for compiling, and that process actually includes assembly language. We saw that whole process that goes through in assembly language was one of the steps. So it actually converts everything to assembly language at some point, and then it goes from there. And so in order to actually incorporate directly assembly language, the IDE needs to be modified in order to accept assembly language files, .s files. The GCC standard uses .s files, not .S files for assembly files. So we're going to go with the GCC standard that uses the .s files. Okay, so we need to modify the IDE to be able to accept these files to be incorporated when you do your build. When you have a program and you want to build it and load it onto your Arduino. So the procedure that I'm going to take is documented in this particular link, so you can go there. And it's particularly defined for Mac OS, but it also applies to others. So the approach I'm going to talk about basically comes from this. So that's where I'm getting my source. But you can, but I'm going to actually make it more abstract. I'm going to make it apply to other the other platforms like Windows and Unix, Linux, not just Mac OS. Okay, so even though this was specifically written or primarily written for Mac OS, it also applies for the other OSs as well. So there are a number of steps, 15 to be precise, that are required to go in order to get a modification of the IDE. So let's take a look at these steps. Many of these steps are quite simple. Some of them take a little while, but it's all very straightforward for the most part. Okay. When I first started using the assembly, someone else had done this for me and just gave me the fruits of their labor. Well, it turns out you can't always rely on other people to do stuff for you like that. So I had to learn how to do it on my own. And even though I'm a doctor, Dr. Paz, Dr. Zap, even though I'm a doctor, have a PhD in electrical engineering, there's stuff like this that I just don't do very often. And so it's stuff that I don't keep up with. Even though I have been doing assembly language probably longer than you've been alive, for many of you, especially college students, I may have been doing this for longer than you've been alive. It's not the kind of stuff I do very often. And so, and things change and different tools and stuff. And so, in some sense, I'm an old guy. And I may not look that old, but actually I'm in my 50s. I probably am older, old enough to be your dad for many of you. But if I can learn how to do it as an old guy, you can, with your fresh, young minds, you can learn how to do this. So buckle your seatbelt. We're going to march right through these steps. So the first step is to go and to get the source code for the Arduino IDE. Okay, so this is where that source code can be found, and you can find it for Mac, Linux, and Windows, the various Windows varieties. So you download the source code, and you extract the zip file to obtain the folder Arduino Master. So when you extract that zip, or when you unzip it, you will get this folder, Arduino Master. Okay, so within that folder, if you dig down, you will find the sketch.java file. And so if you go inside the Arduino Master folder, if you look in the app folder, inside the source folder, inside processing folder, inside the app folder, you'll find that sketch.java file. It's just a text file. So you open it up in a text editor. Okay, so in step 4, we need to insert the .s capability. Okay, the .s capability is not automatically allowed. Okay, so we need to just insert it. Now there are 2 places in the sketch.java file that we need to change. So first we do a search for sc.isExtension C. Okay, you just in your text editor you do find and you type this in, and when you do that, it'll take you to this. Okay, it'll take you to this section of code, and I have no idea what the line number is because again every edition of the Arduino IDE you have different line numbers, so I don't know what the line numbers are, but this is what the code around that looks like. Okay, so we have all this stuff, and basically what we need to do is we need to insert in here this code. Okay, so as you can see, the Arduino IDE accepts C files, it accepts C++ files, and it accepts header files. So we need to modify that line so that it can include .s files. And notice we use .s again according to the GCC convention. Okay, so we just modify that one line to allow it to accept .s files. So again, that's part of inserting the .s capability. So that's the first search. Again, this needs to be done in two places in that. So the next thing we search for is this string, open and close brackets, get extensions, open and close brackets. And when you search for that, you get this, and we have this code, and we need to insert in here. So notice again we have INO file, PDE file, C file, C++ file, H file. We need to have S file in there. Okay, we need to insert S, and this has these curly quotes, but you should just be regular quotes. I don't know why it inserted curly quotes for me, but anyway, so basically you just need to make sure that you can do S files in here. So those are the two changes we need to make in this, very simple changes, and then we save the file. Okay, we save that file. So we just modified the sketch.java file, and we did so in just two places. Okay, and again, the whole point of that was just to allow S files. Everything else about assembly it already can do. So all we have to do is just allow it to access those files. Okay, so steps 4 and so actually that should have been step 4 and 5. Step 6 now is we need to open this file, compiler.java, which can be found in the folder Arduino Master, app folder within that, source folder within that, processing folder within that, app folder within that, debug folder within that. We have this file, compiler.java. Okay, and then you search for this string, compile files, and you're going to do a search for that. What comes up following that is some code that includes find files in folder. And it'll have things in quotes. It'll have, again, things like C and C++, and so forth. And it'll actually have S in there, but it'll have capital S. So change that from capital S to lowercase s. Okay, so this you will need to do, and you'll actually need to repeat this 4 times altogether. So in this compiler.java file, we'll need to make this replacement 4 times and then save that file. Okay, so again, in this case, it already assumed that you could use capital S files, but we need to change it so that it uses lowercase files, again, according to the GCC convention. Okay, so you need to modify 2 files in all of the stuff. So if you looked in that Arduino master folder, you have all these folders and folders within folders, and there's a lot of stuff in there. Okay, we only need to change 2 little things. Okay, 2 little files. All right. So that's the first 10 steps. Step 11 may or may not have to be done. You may already have this done, and it's not an issue. But make sure that you have a recent version of the Java platform on your system. So you can download the Java platform for your system from this Oracle site. Okay, So you just make sure you download that and you install it in your system. Okay, so that's just make sure, again, a lot of the Arduino IDE is written in Java. Okay, so you're just making sure that you have the Java platform, because we're going to compile this now, and it's going to be compiled, and it's when you compile it, it needs a Java compiler. Okay, so not only do you need a Java compiler to do all this stuff, but you need a Java command line tool to work with. Okay, so I recommend using Apache Ant to do the Java command line. Okay, so there are other Java command line tools, but I recommend Apache Ant. And the reason I recommend that is, again, it's cross-platform. It's available for Mac, Windows, and Linux. So the same tool, and so I can show anyone that's using a Mac, anyone that's using Windows, anyone that's using Linux, how to do this process, because we're using cross-platform tools all the way along. Okay, so for Windows, there is this, and actually for Windows and for Linux, you can use this information. This link will take you and help you to install Apache Ant in your system. Okay, for Mac users, Apache Ant is already installed unless you have OS 10.9 and above. For some reason, Apple, in their wisdom, decided to stop including Apache Ant in their distributions for Mavericks and above. So if you have Mavericks as your operating system, that is OS 10.9 or above, then you need to install Ant. And the easiest way to do that is using something called Homebrew. So to install this, you would use in a terminal window in Mac, open up a terminal window and execute this command. Okay, so you can just copy and paste this command, this Ruby command. And so what this will do is it will install something called Homebrew on your system. So it's like layers of things we're doing here. But you install Homebrew. Okay, when you run this command, it will install Homebrew. Okay, when it's done executing, then you run this command, install Ant. And when you do that, it will go through and install the Ant environment, or the Ant command line tool. Okay, so these are two separate commands you would execute in the command window. So that's how it works for Mac OS 10, and it works for any version of Mac OS 10. In fact, it also works for this same approach works for Linux as well. In your command window, then, you would move to wherever you have this directory. So you would need to do like a CD or whatever it is that you use to move to a different directory. And you're going to move to the Arduino master directory and build. So wherever that Arduino master is located, you need to find where that's located and then move to that directory, and then move within that directory to the build directory or the build folder within that directory. Okay, so that's the next thing you need to do, and you need to do this whether you have a Mac or a PC or Linux or whatever. Okay, once you're in that folder, that build folder is a build file. So if you do ant build, it'll go through and it'll do a bunch of stuff. On your command line window, you'll see all kinds of stuff. So when I say command window, in Mac, that's the terminal window. In Windows, that's a command window, and so forth. You're going to see all this stuff. It's going to say it does this, did this, blah, 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 a lot of stuff. And it'll take, to do this build, it will take probably, I'd say, about a minute. About a minute to do all this stuff. And so sometimes it kind of sits there for a while. You don't know if it's doing anything or not, but it'll finish, and hopefully you'll see it'll result in this. It'll say build successful, okay, which means it built the Arduino IDE with those changes that we made. Okay, it builds the Arduino IDE. Now it turns out that in order to actually use the Arduino IDE, in addition to the part that needs to get built, the Arduino IDE actually is a package that includes a lot of other stuff. It includes help files, it includes sample code, that, all of those things are all packaged together. And so it's not just a matter of the executable portion that you need. You also need all of that other stuff in the full distribution. And so you need to package the Arduino IDE using this command, ant dist. So this is the distribution. So it'll start running when you execute this command from the command window. It'll do a bunch of stuff, and then it'll come up and it'll ask you to enter a version number. Okay, it'll ask you to enter a version number and give you a suggestion. For example, it'll give you this as a suggestion. Okay, so I recommend that you take whatever it gives you and then tack on ASM. So for example, you might enter this 1.0.5.asm. So the ASM is to help you remember that this is a build that includes the ability to do assembly language. You don't have to do it this way. You can actually just enter that number directly or 1.0.5 directly, but anyway, I recommend that you do something like that. Okay, and so you want to use the build number according to whatever build you've downloaded when you downloaded it. So it'll recommend something for you. So when you do this, and after you've entered in that version number, then it'll run and it'll do a bunch of stuff, and at some point it'll sit there for a while, and it altogether takes about 5-6 minutes, something like that, to do this. So don't expect it to just happen like that. It takes a little while, but when you're all done, it should say build successful. And when it says build successful, it'll basically create a zip file that has your Arduino IDE and all the package of stuff that's with it. Okay, so it'll tell you where that zip file is. So, okay, once that has happened, then the Arduino IDE can be found in that zip file that's created. So you would unzip the file and install the application in some reasonable place in your computer, like your applications folder or whatever. Okay, so and in fact, you can actually replace any other Arduino IDE that may be on your system with this thing that you've just created, because this thing that you've just created uses the most recent version of the IDE, and it incorporates the assembly language, and it should work just like any version of the Arduino IDE. So the IDE you just created should function just exactly like any one that you are download off the Arduino.cc site, except with the great feature that it accepts .s files. So this is the process we need to go through in order to be able to set up the environment for using assembly on the Arduino IDE. Okay, now that we've done that, let's look at a couple of test codes that we can work with in order to analyze what's going on and kind of see some things, and in particular to test and make sure that what you've done is actually working correctly. Okay, so here we go, sample codes. So again, now we have a new IDE. So it's a little bit different. So here's some things that you need to know about this new IDE. So including the assembly still requires that you use a .ino file. Okay, the .ino file is always needed when you use the Arduino IDE. Okay, and we're going to see that sometimes your .ino file can be blank, but you still need one. Okay, to do assembly, you're going to have a .s file, and you may also need a header file, a .h file. It may or may not. Okay, so the .s and the .h files, they need to be created with the same name as the .ino file, and as you know, the .ino file needs to be in a folder of the same name. So you have a folder with a name, the .ino file has the same name, and the .s and .h files also have to have the same name. Okay, and those files need to be created in the text editor. Arduino IDE does not really do .h and .s files, so you just create them in some text editor. And in fact, what you can do is you can actually start with a .ino file for whatever program you're working with, save it, and then go into the folder where that .ino file is and just make 2 copies of it. And name one the same file name with a .h, the other with a .s, and then if you close your Arduino IDE and then open the Arduino IDE again with the INO file. When you open that INO file, it will open the other files, the .h and the .s, and then you can edit the .h and the .s in the editor of the Arduino IDE. Okay, so all the files also need to be in the same directory. Okay, so here is a test code. Here is a set of code of the files. Here we're going to have the INO file, the .h file, and the .s file. And all these three are needed to do this code. And basically we're doing the blink function, but we're doing it now in assembly. And in this first example, we're going to show using both C and assembly. Okay, so it's using both C. So we're going to do part in C, part in assembly. We're going to basically define subroutines that the C file or the Arduino IDE file calls, and it calls the assembly. So in this ASM test.ino file, this is basically what's in there. Not very much. Okay, so it's going to include the header file, and here's the code. So in our setup program, we have this init function. So this init function is actually going to be defined in our assembly code. And then we have our loop function, and we have this function LED, which again is going to be defined in our assembly code. Delay is the regular delay function that we have in the Arduino IDE. Okay, and so so we basically set the LED value to 0, delay, set the LED value to 1, delay, and so forth. Okay, so this is what happens. So it's our basic blink function, but it uses these assembly subroutines. Again, you can do the blink function otherwise, but this is just used to kind of give you the feel for what it's going to look like to do the to combine all the various parts. And so you could actually test this and run this. Here's our header file. Okay, so first we have if-def assembler. So if the assembler is defined, then you're going to do stuff. In this case, this is the assembler stuff that happens only with the assembler. In our case, we're not going to do anything here. Else, okay, and then we do the stuff that's needed for the C portion. And in the C portion, we're going to do two things. We're going to include stdint.h, and then we're going to define these two functions, LED and ASM init. Okay, and here's how we define them. Extern C, and this is how we define them. So, and then here's our end if. Okay, so if there are specific assembler requirements, it's going to do this. Otherwise, it's going to do this. Okay, so that's our header file. And then here is our assembly code. So notice here is ASM init. And notice it's very short. Okay, and here is our LED function. Here, again, it's fairly short. And then we have another function that we've defined here. Or it's not really a function, it's actually a part of the LED function. Okay, and so that's the code. And again, don't worry about understanding what's going on in this function. This is the function that's needed to do that. So you can see the kind of thing, and again, we're going to get into what all of these commands mean in our next lecture. But for now, we have this. You can see that this simple function has these simple programs associated with them. So that's the first test code. If you enter these three files, then you can run them, and it will do the blink function, the blink program. Okay. We're going to do the blink program again. This time we're going to do it only in assembly. Okay, so here's my INO file. I still need an INO file. Okay, but in this case, blank, nothing there. Okay, here's my H file. Actually, I don't even need an H file in this case. Don't even need an H file. So you could choose to have one, and it would be blank, or you can choose to not have one. And then our code, so this is in our .s file. Here's our code, and the code actually goes on for several pages. Okay, so there's quite a bit to the code, and again, it's not important that you understand the code at this point, okay? But understand that you can do the entire function all in assembly language. So what I've just shown you is the code that does that. So that's our test code number 2. Test code number 3, we've actually seen this kind of thing before when we looked at the motivation for using the C programming instead of just the Arduino IDE. So in this case, I'm actually going to do the same code 3 different ways. So I'm going to do it using the Arduino IDE. Okay, so in this, I call this speedarduino.ino. So it's basically, notice, it's basically turning bit 13 on, digital pin 13 on, then turning it off. So that's the LED on the Arduino. And so it's turning it on and off as fast as possible. Okay, so that's how we do it in the Arduino IDE. Okay, so the same function, we're gonna try to turn them on and off as fast as possible in C, and this is what the code looks like. Using C, again, we're using registers. So pin 13 is in port B, pin 5. So here's how we set port B, pin 5, to be an output port. So that's basically equivalent to this. And then in this loop, we have this odd thing that we're having a while loop, 1, which means it's always doing, this is an infinite loop, and this is also an infinite loop. But it turns out that this infinite loop, which is part of a function, actually runs slower than an infinite loop that's defined by a while function. So it's the difference between a jump and a relative jump in terms of the assembly code, and it makes a difference. So here, what am I doing? I'm setting pin 5 of port B. Then I'm resetting or clearing pin 5 of port B, and then I'm just continuing to do. So I'm setting and resetting, setting and resetting. Okay, and so here I'm doing it directly using the registers. Okay, and so I'm doing this in C. So these two programs, they have different names because they're doing different things, right? I mean, this is using a different environment, different set of code than this. Okay, so I'm using the registers here. But they have the same function. They're just switching the LED as fast as possible within that environment. So Arduino IDE, C, and now we're going to do the assembly. In this case, here is our INO function. It's blank. There's nothing there. It needs to be there. Here is our assembly function. And notice here's our setup routine. Here's our loop function. Okay. Again, in this case, it's short because it's a fairly simple function. You turn an LED on and off. We don't have to do a whole lot of other stuff. Okay. And so again, it's very short. And again, you don't need to know the details of what it's actually doing at this point. But needless to say, this code will work. So how do the 3 compare? So here are the 3 options: the Arduino code, the C code, and the assembly code. In terms of when it's compiled, the Arduino code takes up 874 bytes, the C code 472, assembly 472. So these actually have the same footprint, same size when compiled. So notice that this is not the amount of space in the file. So the .ino file, that's not the size of the INO file. That's the size of the code that's been compiled down to binary. So this is the size of the binary file that's used. Okay, and in this case, these two happen to be identical because they're actually doing very similar things. In fact, if you looked, well, anyway, they're doing very similar things. Okay, just doing it a little bit differently. And the speed. Okay, these are the speed values, and you can see this is as fast as you can go in the Arduino. This is as fast as you can go using that C program. This is as fast as we can go using that assembly program. Okay, and so these are scope traces that we can get looking at those particular programs as they run. So here we have microseconds. This is also microseconds. This is also microseconds in terms of that time scale. So overall, this has a period of 121 kilohertz for the Arduino. For the C, it's 2.66 megahertz. So this is a lot faster using C. Okay, a lot faster, more than an order of magnitude faster. Okay, more than 10 times. It's more like 20 times faster. And this is even faster. Okay, this is even faster, 4 megahertz. So, and if you think about the clock speed of your Arduino, 16 megahertz, that's basically 16 megahertz divided by 4. Okay, so that's pretty good. It basically takes 4 clock cycles to do 1 period, which you would expect. I mean, it takes 2 clock cycles, one to switch, one to set, one to reset. So you know it's got to take at least 2 clock cycles to do that, and then 2 more clock cycles to do the bookkeeping. And so so basically each time through the loop requires 4 clock cycles. 4 clock cycles. So that's pretty fast. And it's basically as fast as you can go, 4 megahertz. So this is our brief introduction into using assembly on the Arduino. Again, when we come back next time, we're going to look in detail at the assembly codes used by the ATmega 328. Thanks for watching.